Okay, so let's try to recap what we did last time with an example. An example. So again, we're in this new phase in probability dealing with random variables. And in particular, we've been going over discrete random variables. Discrete meaning that the values themselves, that the function that the random variable attains are whole numbers, are discrete numbers. And we discussed what a Bernoulli random variable was, which is a one single trial, one single experiment that has two different outcomes with probabilities that add up to one. And then we spoke about binomial random variables, which is more than one Bernoulli random variable being applied at the same time. Again, with two different outcomes and probabilities for those two different outcomes. And we discussed what's called the probability mass function, which just explains what the probabilities are for every value that the random variable attains. So what if I give you a problem like this that says, suppose 3 fair dice are rolled. What is the probability at most 1/6 appears? Key phrase here, at most 1/6 appears. So the first thing we have to consider is, what kind of random variable is this? How would I define my random variable? So we have to, let's define our random variable x. So how would you define your random variable? The time that the 6 appear, right? So we can say as the number of times that a 6 appears when rolling 3 fair dice. Okay, so that's very good. Thank you, Daisy. Yes, so we defined x as a random variable that tells you the number of times that a 6 appears. So what are the values of x? What are the values? So within those 3 fair dice being rolled, what can x attain? 0, 1, 2, and 3. Very good. So x can be 0, meaning that there are no 6s that appear. X can be 1, which means that there's 1/6 that appears. X can be 2 out of the 3 fair die having a 6. And then x can finally be 3. Right? So these are the different values or scenarios that we have when we talk about rolling a 3 fair dice and seeing whether a 6 appears or not. Now, this phrase, at most 1, includes which one of these values? If you roll at most 1, correct, Hijab, that's right. So that means that these two here, these two values constitute the scenario that you have at most one. At most one means it could be 0 or 1. So this includes at most 1. And I should write this as a word. At most 1, 6 appears. Now, on top of this, so far we're breaking down our problem into defining a random variable very explicitly, which is probably the hardest part here, is being able to identify and define a random variable, which we did. Now we know all the values of this random variable. Now the question becomes, what kind of random variable is x? What type of random variable is x? So what is x? Well, there's only two that we've discussed really so far, right? So it's either a Bernoulli or a binomial. So the reason why it's not a Bernoulli is because we're applying multiple trials, right? So rolling one fair dice, you can consider it as a Bernoulli, but we're rolling 3 fair dice. So this should be a Bernoulli. I mean, binomial, pardon me. This should be a binomial. It's a binomial random variable. So once we know that's a binomial random variable, then we know the parameters, right? What are the parameters? So what are the parameters? So what are my parameters? Well, I know that n is the number of trials. Well, we have 3 of them. What is p? Remember, p represents the probability of a success. So this is where a choice comes into your into this point right here. You either make a decision. What do I constitute as a success? Well, I constitute the success. I may consider it as the probability of rolling a 6, right? So my success, quote unquote, is rolling a 6 because that's what the problem is asking. So what's going to be my failure? My failure is not rolling a 6. If I don't roll a 6, then what am I rolling? A 1, a 2, a 3, a 4, or a 5. That's what that means, right? So this is my failure, and this is my success. That's how I defined it. So to roll a 6, I have 1/6 of a chance because I have a fair die, right? Now, what is 1 minus p? Well, it's the failure. So I have 5 other faces of the die that can roll not a 6. So I have 5/6. Now, what is x? The little x, not big X, okay? This is the little x. This is the number of successes. It goes back to what we defined the values of x to be. So x could be 0 or it could be 1. So the number of successes that I'm considering is when you have 0 6s and when you have 1. So you can have multiple values of x, right? In this case, that's what I have. So the probability of having at most 1/6 is equal to the probability that x equals 0 or the probability that x equals 1. Of course, these are mutually exclusive events. If I have 0 6s, I can't have 1 6 as well. So these are mutually exclusive. Which means I can add them separately. The probability that x equals 0 plus the probability that x equals 1. And we know, because it's a binomial random variable, we know the probability mass function. We know what this is going to look like. This is, again, remember we write it a little bit more succinctly by just having a lowercase p for probability and 0 being the value of x. Same thing goes for p1. So recall for binomial random variables, the probability that you get k is the binomial coefficient and choose k, p to the k power 1 minus p to the n minus k power. This is something that you have to remember about binomial random variables. That's the probability mass function. Now, all I have to do now is use this same formula and plug in the numbers that I already know. I know what k is going to be immediately, 0. I know n is 3. I know p is 1/6, and I know 1 minus p is 5/6. And then the exponents are taken care of as well. So p of 0 is going to be 3 choose 0, 1/6 to the 0th power multiplied by 5/6 to the 3rd power. If you study this correctly, you see that this becomes 1, this is 1, and what do I have? I have the probability of having not a 6 3 times in a row. So that's 5 6 cubed. So it's consistent. Even if I didn't know the binomial random variable probability mass function, I can still figure it out. Plus 3 choose 1 times 1/6 to the 1st power multiplied by 5/6 to the 2nd power. So I'm able to do that. And I can also, again, put this in my calculator. So I'll do that really quick. So again, we go to distribution, second vars, go all the way down until you see binom PDF. Tells me the trials, I have 3 trials. The probability is 1/6. And the x value, for now, I'm just going to plug in 0 and see what that gives me. And let me see if I can convert this into a fraction just to help out. Okay, so the probability of this is 125 over 216. Now what you can do, instead of going all the way back, you can copy this. And you see the arguments inside this function. The first argument, or the first coordinate, if you think of it, is n. The second coordinate is p, and the last coordinate here is x. So I want x to be 1 in this case. So when I press this and I convert this to a fraction by going math, enter, enter, I get 25 over 72. So I can make the calculator work for me. So if I press 25 and then I add this one here, what do I get? And I go math, enter, enter. I get 25 over 27. That's what I get. which is approximately 0.925. And it looks like this repeats. Yep, so this repeats. Okay. So we've found the probability. We found the probability of rolling at most 1/6 when we roll 3 fair dice. Any questions about this? Is this clear to everyone? This is a binomial random variable example. Okay? Okay, great. Great. Now, I want to discuss 2 extra things about random variables. Okay, so the first thing is what's called a cumulative distribution function. This is also known as the CDF. So we're going to have a lot more abbreviations coming up now. We have the PMF, which is the probability mass function of a random variable. And now we have what's something called the CDF, which is the cumulative distribution function, which is related to the probability mass function. Now, let me just tell you what that is. The probability mass function, the notation for it is the following. So we're giving uppercase F for this, and the X is the value of the random variable. It's the probability that your random variable is less than or equal to the particular value that you're considering. So that in itself is the cumulative random distribution function. Now, the importance about this is that every random variable has its specific cumulative distribution function. So, for example, suppose X has a PMF of, suppose I have P of 1 being a fourth, P of 2 being a half, and P of 3 being an eighth, and P of 4 being an eighth as well. So this is my probability mass function of a particular made up random variable. It's not considered, in this case, we're not considering what kind of random variable it is. It's just a random variable that has these probabilities associated with these values for X. So if I were to sum them, so notice, what do I notice? Is this indeed a legitimate random variable? Well, let's check. How do I check? If I take the probabilities and sum them all up, does this equal 1? Well, 1/4 plus 1/2 plus 1/8 plus 1/8. Well, 1/8 plus 1/8 is a fourth plus a fourth is a half, plus a half is 1. So this checks out, right? So we always have to do that just in case, just to make sure things are okay. Now, what is f of 1? Now let's consider the PDF. I mean the the CDF. So what are the different values that we have? Well, we can let's start with 0. what's the probability that my x value is less than or equal to 0? Well, this is an easy one because we don't have a value for x being 0. So the probability of that happening is 0. Now, what is the function of the CDF of x when x is 1? This is the probability that the x value is less than or equal to 1. It may not seem that necessary to have less than or equal to a value of x, but particularly when we talk about continuous random variables, this actually becomes very helpful. But we introduced this idea of CDF from the beginning with random variables, discrete random variables. So what is this here? So x could be what? If x is less than or equal to 1, then x can be 0 or 1, correct? That's another way we could consider this. The probability that x is 0 or the probability that x equals 1. But the probability that x equals 0 is 0, and the probability of x equals 1 is 1/4. So far, you're like, this doesn't really matter so much, it seems, but it does. Now, what if I want to find the probability that x is less than or equal to 2? So what am I going to do here? Notice the word cumulative is embedded in this abbreviation, right? So I am, in a sense, I am accumulating all the probabilities for 2 and before 2, like 1 and 0. So then I'm accumulating all these probabilities and adding the last probability of it, x being 2, which is a half. And as Sering just mentioned, yes, that's exactly right. 3/4. It's going to be 3/4. And then f of 3 is p, the probability that my random variable is less than or equal to 3. So I'm going to add up all the probabilities that when x equals 3 and when x is less than 3. So that's going to be the probability of 0 plus the probability of 1 plus the probability of 2 plus the probability of 3. So I already know what this is. This is the cumulative function for 2, which is 3/4. And the probability of 3 is 1/8. So when you add these up, what do you get? 7/8. And then lastly, this is my last value. What if I accumulate all the probabilities for the random variable being less than or equal to 4? Well, when I do this, I exhaust all my possibilities for the x value, right? Attaining its particular values that I have, 1, 2, 3, and 4. So this is the same thing as saying the cumulative function defined at 3. Let me just make that a little bit more explicit. So that means that I can have my probability being 0, the probability being 1, the probability being 2, the probability being 3, and the probability being 4. And this whole thing here is exactly what I just figured out in the previous problem here, which is the cumulative function defined at 3, which is 7/8. And then I'm adding the probability of it being 4, which is 1/8. And it's a 1. Okay, does that make sense? So now we're adding a bit more information that we can extract or describe a random variable. And this is another way to do so with the CDF, which is related to the PMF. And we can also graph. We can also visually graph the CDF. Okay, so this is going to be my f of x, little x. This will be my little x. And so I'm going to represent the axis here by every tick mark being a 1. So this is 1, 2, 3, 4. And so what is f of 0? Well, f of 0 just starts at 0, correct? So I just have a point here on 0, really. Now, what if I have what if I define f of 0.5, for example? What would 0.5, f of 0.5 be? Meaning, what's the probability that my function here attains 0.5 or less than 0.5? What would that be? It's 0, correct? It's not possible in this problem. But the thing is, this is going to be 0 for every value less than 1. So in reality, I'm going to have a function, a constant function 0, and an open circle here. Now, what happens when f, like I saw, f of 1 is a fourth, right? So let me draw this axis here. 1, this is a half. This is a fourth. This is 3/4, 7/8. So what happens when f is 1? Well, we know that's going to be a fourth, right? So f of 1 is a fourth. So we have this dot here. But what happens when f in the in-between values? Do you see this? Again, this will make much more sense when we talk about continuous random variables. But for this case, we're only dealing with discrete numbers, right? So we only consider the 1, the 2, the 3, the 4. But the CDF is an accumulation, right? So we're also considering, in a sense, we're considering values in between. But the way we deal with that is a bit different in the discrete world. We just say, so if I say, for example, f of 1.5, what's the probability that x is less than or equal to 1.5? Well, our x values can't equal 1.5. So this statement here is reinterpreted, right? It's reinterpreted as the probability that x is less than or equal to 1. Because you can never have 1.5, 1.3, 1.7. But this inequality contains this idea that I can be equal to 1 or less than 1. And I already know what that probability is. It's a fourth. So I'm just trying to show you guys that the reason why we have this kind of representation when we graph a CDF, in particular for, it doesn't round up, no. Okay, yeah, it maintains itself. So then at f of 2, what's f of 2? It's 3/4, right? So 3/4, I'm going to be right here. That's for exactly at 2. But for everything in between 3 and 2, it's a straight line. And then finally, from 3 to 4, I get 7/8, right? I think this is a little too. Three to 4, I have 7/8 right here. I think that's a little too much here. And then finally at 4, I get 1. So what I get, what do I notice? Note, CDF of a discrete random variable is a step function. And in particular, you can think of this as an piecewise function. Okay. So I can represent my CDF as a step function visually, or as a piecewise function. It's 0 whenever x is less than 1. It's a fourth when x is greater than or equal to 1, but less than 2. You see, it's strictly less than 2. Then it equals 3/4 when x is greater than or equal to 2, but less than 3. And then we get 7/8 when x is greater than or equal to 3, but less than 4. And then finally, when x is greater than or equal to 4, the cumulative distribution function is defined at 1. Okay, so we can represent our CDF as a visual graph or as a piecewise function. And again, this will become more prevalent, particularly when we talk about continuous random variables. Okay, so that's the CDF. And just quickly, we can also graph the PDF. Pardon me, the PMF of X. For continuous random variables, the PMF will transition to the abbreviation PDF. But we're not there yet. So what does the PMF of X look like? It's a similar setup with the horizontal axis. It's 1, 2, 3, 4, right, for X. And then the vertical axis is the probability of X. So what's the highest probability that we have? Is a half, pardon me. So it's a half. So I'm gonna write this as a half. This is a fourth, and this is an eighth. Now, there's different ways to represent this graphically, but normally people use like bar graphs for this. So at 1, the probability at 1 is 1/4. So I draw this little bar here. This is a fourth. At 2, I have what? Was it a half? Yeah, it's a half and an eighth and an eighth. So I have a half. And at 3, I have an eighth, and at 4, I have an eighth. So do you see that there's more than one way of understanding what a random variable is? We have the description of the random variable based upon the values of the random variable and their specific probabilities. So you can visually look at it and be like, okay, so this is the distribution. The word distribution appears a lot in probability. This is the distribution of the probabilities of this random variable. This is how it's distributed, and you can visually see that. Or you can view it from the perspective of accumulation of those probabilities, such as a CDF. or you can look at it as a defined function for the CDF, or you can look at it as a values as the PMF. So the PMF can be written as functions. The CDF can be written as a function. The CDF can be expressed as a graph, and the PMF can also be expressed as something visual. Okay, so these are 4 different ways that we can describe a random variable. And this becomes much more powerful when we have more complex random variables. Okay. So the next thing, so that's one of the things, right, that I wanted to discuss, CDF, the cumulative distribution function. And now I want to talk about something also very important in random variables, which is called the expectation. Expectation. Has anybody heard what expectation means in context of probability? It's also referred to as AKA the expected value. And there's one more word which you probably all have heard before. I think it defines itself. What do you mean by it defines itself? That the definition is self-explanatory for what expectation is?
I would think so.
So what is it?
It's the value that one can expect after doing n trials and knowing the probability.
Okay. Do you know another word for that? No? It's the mean, or also known as the average. It's the average value, right? So it's what you expect when you perform a certain probability experiment. Hence the term expectation or expected value. So then what's the notation? So if we have let x be a random variable. So if we have a random variable, the expectation is given by an uppercase E bracket x. Now, how do we define expected value? How do you define expected, what the expected value would be given probabilities of the values of the random variable? Well, the way we define it is the following. We take the summation where I goes from, well, it depends what the values are, right? So let's suppose I have n different values for x. So x sub I multiplied by the probability that I have x sub I. This is the definition of expectation. So in other words, the expected value of x is the weighted average of all the possible values that x attains. Okay. So let's see an example of what I mean by this. One second. So suppose, example, let's do this. Let x be the outcome of rolling a fair die, a fair six-sided die. What is the expectation value or the expected value of x? Well, first you have to figure out what's the different values of x. What can x attain? X can be what? 1, x could be 2, x could be 3, x could be 4, x could be 5, or x could be 6, right? The way I define x is the outcome of rolling a fair six-sided die, which could be 1 through 6. Now, what's the probability of me getting an x being a 1? Isn't that the same thing as the probability of me getting a 2, which is the same thing as getting a 3, a 4, a 5, or a 6? So according to the definition of expectation, I'm taking the sum and I'm saying x, or I'm saying I goes from 1 through 6, x of I times the probability of x of I. But that's the same thing as saying the probability of 1 multiplied by 1, 6, plus 2 multiplied by 1, 6, plus 3 multiplied by 1, 6, plus 4 multiplied by 1, 6, and so on. So you have in the top, you have 1 plus 2 plus 3 plus 4 plus 5 plus 6 in the numerator. And the denominator, you have a 6. When you add these up, what do you get? 7 times 3, which is 21. You get 21 over 6. And then when you divide this, what do you get? Well, the 3, right, goes into a 6 2 times, and 7, 21 7 times. And so I get 3.5. So obviously you don't get, when you roll a, in this case, in the discrete case especially, when you roll a six-sided die, you don't never ever get a 3.5, right? So in a way, that's kind of, it's a bit misleading sometimes to say that this is exactly what you're supposed to get or you expect it to get, because you don't get a 3.5. But what this is saying, though, this is saying that because of the symmetry, because every value for every value of x, I have an equal probability of it happening. Obviously, the mean would be right in smack dab in the middle of all of the values that x can attain. X can attain a 1, a 2, all the way to a 6. So what's right in between all these numbers? The only middle number here is 3.5. So it's more than just the expected value of what you're supposed to get when you roll a six-sided die. It's really a number that indicates the possibilities with respect to the values of x. So if I were, for example, if I were to graph the PMF of this particular random variable, what would it look like? So if this is P of X and this is X, so I got 1, 2, 3, 4, 5, 6. What would be the probability mass function? Well, it will be very uninspiring in a way, because all of these probabilities are exactly the same. They're 1/6. And then what is the 3.5 represent? The expected value or the mean. Another way to interpret the mean or the expected value of a random variable is, if you were consider this to be a scale, right? And you have weight. These are different weights, and they're equal weights, and you wanna place the scale in you wanna place a certain like a fulcrum at a particular point so that it balances out the weights. Where would you put that point? Well, you would put it exactly where the expectation is, right in the middle for this particular problem. There might be other PMFs that are not symmetric in this fashion, but you can always find a particular point where you can balance out the probabilities, and that's what the expected value also can represent. Okay. So any questions about this particular problem? Good? Make sense? So they are not all symmetric. Of course not. Didn't we show something that's not symmetric? Look at this. This is not a symmetric distribution of probabilities. This is, though. This is very, like, it's just all the same. It's a constant, right? It's fair. This is a fair-sided coin. Every value of this random variable has the same probability of appearing. So this is almost a very, a very simple case, But we have a lot of these things that happen where the probabilities are not symmetric. So then the question would be, for this problem, going back to the example that we have of these probabilities, right? The probability of 1 being a fourth, the probability of 2 being a half, the probability of 3 being an eighth, and the probability of 4 being an eighth. What would be the expected value of this particular problem? So let's go back to the example. So given example of X above, what is the expected value? So how do I do this? How do I find the expected value for this random variable? In other words, I want to figure out, where would I put that fulcrum? Where would I put that little thing to balance out the scale here with the weights, with the probabilities? Does everyone follow me? I have only 4, right? I have 4 values of X. What are they? Well, I can have a 1, so I'm multiplying by the probability of getting a 1, which was what? A fourth. I can have a 2, and the probability of me getting a 2 is a half. I can get a 3, and the probability of me getting a 3 is an eighth. And a 4, and the probability of me getting a 4 is also an eighth. So when I add these up together, what do I get? So I get 1/4 plus 2 times a half is 1 plus 3/8 plus a half. And I get 2.125. And as a fraction, that would be 17/8. This is my expected value. This is the mean. Again, this is the mean. This is the mean of my random variable, or the average. So if I were to place this at 2.125 somewhere here, this would balance out the distribution of the probabilities. So does that make sense of how to compute expectation, how to compute expected value? You're taking all the values of x that the random variable attains, and you're multiplying for every value, you're multiplying each of its probabilities and adding those up. And that would give you the expected value. Okay. Any questions about this, guys? Okay. Now let's revisit the Bernoulli random variable. So what's the Bernoulli random variable? Remember, it's defined as, we'll give it a 1 if success occurs, right? Or we give it a 0 if failure occurs. Now, what was the PMF of x if we had a Bernoulli? Do you remember? So we have either x equaling 1. So either I have a success or I have a failure. Do you guys remember what the probabilities were? We just gave it a little p, and p was a number between 1 and 0. So we gave the probability of having success a p-value of between 0 and 1. So if my probability of having a success is p, then my probability of having a failure is 1 minus p. Okay, and now the question I'm going to ask is, what's the expectation? What's the expected value of a Bernoulli random variable? Well, I only have 2 possibilities for x. X could be 0 or x could be 1. And what's the probability of me getting a 0? Well, it's 1 minus p. And I have to add that to the probability of me getting a 1, which is a p. So the expected value of a Bernoulli random variable is simply p, which is the probability of getting a success. That's as simple as we can get. A Bernoulli random variable is as simple as we can get in terms of discrete random variables. Okay, again, we're building up ways to describe random variables. So one way is to use what's called the PMF. Every Bernoulli random variable has this structure behind the probability distribution. And every Bernoulli random variable's expectation is equal to the probability of getting success, which is p. Okay? Now that we revisited the Bernoulli random variable, let's talk about the binomial random variable. Now remember the binomial random variable. So again, this is when you have the parameters, right? We have parameters. What are my parameters? We have n, we have p, we got 1 minus p, right? So n are the independent trials that we have. P is the probability of success. And 1 minus p is the probability of failure. Now, what was the PMF again? What's the PMF of my random variable x? So x can be something, right? X can attain the values from k through 11, n. Why did I say 11? K could be anything from 1 through n. Because remember, x represents the number of successes, whatever that means in the context of our problem. So if we have n tries, our number of successes could be 0 out of the n, 1 out of the n, all the way to n out of the n, right? So our PMF, if we have k successes amongst the n trials or the attempts that we have, it's equal to n choose k, p to the k power 1 minus p to the n minus k power for k equaling 1 all the way through n. We know this, right? Now, again, my question, so this is something that we already know. My question to you guys is, what's the expected value? What would be the expected value of the binomial random variable? Again, the definition hasn't changed. So in this case, because I'm using k, I'm going to use k as my index. So k can go from 1 through n of x sub k, p of x sub k. Which means what? Oh, I could just write this as k. Because my values of x can be anything from 1 through k, right? No, it's not going to be 1 over n. Because in this case, it's not necessarily true that every value of x has an equal probability of occurring. Every value of x, which is k, right, has probability of k occurring, which is given by this. So in reality, this is what I have. It's much more complicated than what you may anticipate. This is n choose k multiplied by p to the k 1 minus p to the n minus k. So I'm just gonna warn you guys, there's a bit more algebra here coming up. Okay. Oh yeah, and this should, so k actually goes from 0 through n, not 1. Because you can have 0 successes, you can have 1 success all the way to n successes. So be careful with that. So this should be a 0. Now let's unpack this a bit. Do you guys remember what n choose k was? How we defined it using factorials? This is k multiplied by n factorial over k factorial times n minus k factorial times p k times 1 minus p to the n minus k. Okay. Now, what happens here? So bear with me. You see there's a k here, and there's also a k factorial here. I can cancel out the k's, but when I cancel the k from the k factorial, I get k minus 1 factorial. Okay, and then I'm going to do the following. Then I'm going to factor out an n, and I'm going to factor out a p. This is k equals 0, right? All the way to n. This would be, if I factor out an n from n factorial, I'm left with n minus 1 factorial. If I factor out a p from p to the k, I'm left with p to the k minus 1, 1 minus p to the n minus k, and I get n minus k factorial. Everyone with me so far? Does everybody see what I'm? Yes. So all I did was I'm using the definition of expectation. I am using the fact that the probability of this value of x is a binomial, right? So I know that what the probability will be. It would be given by this expression here. I've unpacked the definition of a binomial coefficient using its factorials. I canceled out one of the k's. I'm left with the k minus 1 factorial. I factor out one of the n's out of the summation that I have because each of these has an n associated with it. And I factor out one of the p's. So I got a p, an n and a p outside of the summation. And I'm left with this inside here. Now, the question becomes, what is this? What in the world is this here? So if you notice, let's see, I got a 1 minus p. 1 minus. So, okay, what happens here, this is k equal to 0. The thing is, the problem here is that when I canceled out the k here, the 0, k equals 0 is no longer necessary to speak of. And it wouldn't make sense for me to plug in a 0 for k, because 0 minus 1 factorial, that doesn't have a defined, negative 1 factorial is not defined. So actually, we have to rearrange this a bit and call this 1. Because it also wouldn't have made sense to factor out the p and be left with the p to the negative 1 power. Okay, so this becomes, so if this becomes a k minus 1, this here is a k minus 1. That would be okay. And then I'm left with k here and n minus k here. I think that's, yeah. And so now, what is this going to be? This expression here is going to be n minus 1 choose k. This is p to the k. And this is 1 minus p to the n minus k. I think the indices are a bit off. So let me just see one thing. K minus 1. Yeah, some of the indices are off here. Um, let me just see. So when we factor out the k, when we cancel out the k's, this 0 is no longer a 0. Okay, and so actually this index here that was changed from here, from the beginning, from 1. And then what happens is there's a rewriting of it. There's a rewriting of it. So what happens is the k minus 1 idea, this becomes I, okay? So k minus 1 becomes I. This is k minus 1 because I took out the p. And so if that's the case, then k is equal to I minus, pardon me, I plus 1. Okay, so I know this is a little strange, guys, but what I'm trying to show you is that it's just a little bit of rewriting here. This becomes a k minus 1. This becomes p to the I power. And this is I goes from 1, I goes from 0 to n minus 1. Now the idea, what's the whole idea? What's the whole idea behind this? The whole idea is that this here is the binomial, you're summing up the probabilities of a binomial random variable with n minus 1 values. So the idea is that this here is actually applying the binomial theorem. This is p plus 1 minus p to the n minus 1 power. And we briefly saw last time how the binomial random variable is associated with the binomial theorem. If you add up all the probabilities of a binomial random variable, it always equals 1. And that's the idea. The idea is that this becomes 1, and 1 to the n minus 1 power is simply 1. So the idea is that the probability or the expected value of a binomial random variable is n times p. So this is the conclusion. Now here, it's just a little bit of playing around with the indices. And there's a lot of rewriting. So that might be a bit, I understand that might be a bit confusing at first because we rewrote k minus 1 and we rewrote it as I, as another index, which is very common to do in mathematics so that things work out in a very nice way. So we say k minus 1, we call that I. So when k equals 1, do you see that? When k equals 1, if I make k minus 1 equal to I, then when k equals 1, I equals 0. So that's where the index is changed. And then if k equals n, then I would be changed to n minus 1. Do you guys see that? Do you guys how we change the indices here? We changed the indices. Why do we change the indices in this way? So that we can see how it's connected to the binomial random variable. Did you forget to replace the k with I plus 1? Yes. Yes, so if I replace the k with I plus 1 right here, I would get, so let me do this. Let me just rewrite this as n for now. And let me replace this with k equals 0, k equals 1, okay? So then when I change the indices, when I change it, So I'm not going to change it here. I'm going to change it further down. So I'm going to change the indices here. So when I do that, the k minus 1 equals I, right? The k equals 1 becomes I equals 0. The n here becomes n minus 1. And let me rewrite this. This becomes n minus 1 here is okay. Then on the bottom here, k minus 1 is I. So this becomes I factorial. And then k minus 1 here is n minus k minus 1, which is minus I plus 1, minus 1. So again, this is just like technical little details here. And so this is what I get at the end. When I plug in the k here with the I plus 1, right? When I distribute the negative, I get n minus j I minus 1. The idea though is that this here is the, let me fix that for you guys. This here, np, this is the summation of I goes from 0 to n minus 1. This here, this expression is n minus 1 choose I. This is p to the I. This is 1 minus p to the n minus I minus 1. And this here is as if you're summing up a the probabilities of a binomial random variable that goes from 0 to n minus 1. This is exactly the same thing. It's exactly the same thing. And so this here, this summation is the binomial theorem being applied to the n minus 1 power. So p plus 1 minus p to the n minus 1 is 1. So that's why the expected value of a binomial distribution is n times p. So anytime you have a binomial random variable, and you know the number of trials and you know the probability of the success, then the expected value will always be n, which is the number of independent trials, multiplied by p, which is the probability of a success. And this is always true for every binomial random variable. So this is always true, always the case for every binomial random variable. Okay, guys? So that's the main takeaway behind the expected value of a binomial random variable.